If there is a single payoff that depends only on the price of the asset at maturity, it is not necessary to simulate the intermediate values in the trajectory. The simulation of the geometric Brownian motion can be made in a single step. We will now illustrate how to price a European option using Monte Carlo simulation. If there is a single payoff at maturity that depends only on the value of the underlying asset also at maturity, it is not necessary to simulate the intermediate values of the trajectories. The simulation of the geometric Brownian motion can be made in a single step. Therefore, we will simulate only the value of the underlying asset at maturity at t0 plus t. In the Black-Scholes model, this is equal to the initial value of the underlying asset, and then in a single step, the exponential of r, the risk-free interest rate, minus 1/2 sigma squared times t, plus sigma, the volatility of the underlying asset, times a square root of t times a sample from a normal 0-1 distribution. And this will do for capital M simulated trajectories. Then, for each of the trajectories, we're going to compute the payoff evaluating the function g at the value of the underlying asset simulated at maturity. The Monte Carlo estimate of the price of the option again is the discount factor times the average over the simulated trajectories of the corresponding payoffs. The Monte Carlo estimate of the price of the European option is a random variable that is subject to fluctuations. Therefore, the error of this Monte Carlo estimate will be proportional to the standard deviation of this random variable. Using the central limit theorem, the standard deviation is equal to the discount factor times 1 over the square root of the number of simulated trajectories times the standard deviation of the corresponding payoffs. This is the function we use to price a European call option using Monte Carlo simulation. The parameters of this function are the following: S0, the initial price of the underlying asset, K, which is the strike of the option, R, which is the risk-free interest rate, T, the time to maturity, sigma, the volatility of the underlying asset, and finally M, the number of trajectories that we want to simulate. To carry out the simulation, we first generate M samples from a normal 0-1 distribution. Using this random vector, we simulate M trajectories in a single step with the Black-Scholes formula. The payoff of a European call option is the maximum of the difference between the price of the underlying asset at maturity, ST, and K, the strike of the option, and 0. Finally, we compute the Monte Carlo estimate of the price of the option by multiplying the discount factor times the average of the simulated payoffs. The error of this estimate is proportional to its standard deviation. The standard deviation is the product of the discount factor times the standard deviation of the simulated payoffs divided by a square root of M, the number of simulated trajectories.